Spiking neural network models, which capture the collective dynamics of biological neurons, typically exhibit two types of interactions: additive and independent of the neuron's current state, or multiplicative and dependent on the current state. Notably, these two types of interactions are equivalent, provided the intrinsic neuron time evolution is simultaneously modified. This equivalence enables the transfer of theoretical insights and results between spiking neural network models with different interaction mechanisms. Spiking neural networks, comprising hybrid dynamical systems with time-continuous intrinsic dynamics and interactions, have been used to model a broad range of natural and human-made systems, including biological neural circuits and engineered systems. The dynamics of these systems can exhibit novel phenomena not present in smooth, time-continuous differential equations, such as the emergence of linearly unstable attractors and speed limits in relaxation dynamics. Previous studies have demonstrated these phenomena for models with additive coupling, where the coupling strength is constant and independent of the receiving unit state. However, biological neural circuits and artificial computational devices often exhibit state-dependent, multiplicative coupling. By introducing a specific transformation to the neuron model, network models with multiplicative coupling can be equivalent to those with additive coupling. This equivalence has significant implications. Theoretical and practical results on oscillator networks with additive coupling can be transferred to those with multiplicative coupling, and vice versa, by transforming the neuron model accordingly. Furthermore, for technical applications, the choice of coupling type can be made more freely by modifying the neuron model, depending on the particular neuron model and coupling network. To demonstrate this equivalence, the authors consider a pulse-coupled oscillator network with n-dimensional dynamical systems, where the states xi, t, are defined by a dynamic equation. A phase formalism is used to describe the dynamics of the system, where the phase of each oscillator is defined as the time elapsed since the last spike. The authors then introduce the concept of additive and multiplicative coupling, highlighting the implications of their equivalence result for spiking neural network models. In this research, the dynamics of coupled oscillatory neurons are modeled using a system of ordinary differential equations, ODEs, with interaction terms. Each neuron state is described by a variable xi, which evolves according to the equation dxi, dt equals phi, xi, plus c, xj, t, where phi, xi, represents the intrinsic dynamics and c, xj, t, represents the interaction with other neurons. A reset mechanism is introduced, where the state variable xi is reset to a value x reset equals 0 at discrete times t, m when it passes a threshold value x thr equals 1, creating a free period t for each neuron. The interaction between neurons is modeled using pulse coupling, where a neuron that reaches its threshold sends a short-lasting signal to connected units. This work focuses on purely inhibitory coupling, where epsilon1ij is greater than or equal to 0, and sets tau ij equals 0 for simplicity. The effect of neuron j reaching threshold at time tj is an instantaneous, discontinuous change in the state of other neurons xi by a constant epsilon1ij. The resulting dynamical system is of hybrid type, with continuous time-free evolution interrupted by discrete events. The system can be transformed into a phase description using the Marollo-Strogatz formalism, where the phase phi I, t, evolves with a constant phase velocity d phi I, dt equals omega I until it reaches the threshold value phi thr equals 1 and is reset to 0. The interaction between neurons is mediated by a rise function or neuron potential UI, phi I, that is monotonically increasing and twice continuously differentiable. The response of unit I to another unit j reaching the threshold value phi j equals 1 at time tj is defined by the transfer function h epsilon 1 I, phi I, equals u1 I, ui, phi I, epsilon 1, where epsilon 1 is defined as epsilon 1 ij. For a free dynamic of the form dxi, dt equals phi, xi, it is always possible to choose ui, phi I, is defined as xi, phi it, where xi, t, is the free solution with period t. The phase description of the free time evolution is then given by d phi I, t, dt equals omega I equals 1, t, phi I, t plus t, equals phi I, t, where phi I, t, is reset to 0 after reaching 1. This phase description provides a useful framework for analyzing the dynamics of coupled oscillatory neurons. The authors introduce a multiplicative coupling scheme for oscillators, where the state of the receiving oscillator is linearly related to the state of the sending oscillator, as described by equation 17. This leads to an update rule, equation 18, which differs from the additive coupling update rule, equation 6. To describe inhibitory multiplicative coupling, the authors modify the Marollo-Strogatz formalism, defining a multiplicative coupling transfer function, equation 19, which expresses the effect of a neuron resetting at time t on the phase of a connected neuron. The free time evolution is defined by d phi I, dt equals omega I, with a reset to phi I equals 0 upon reaching the threshold value phi thr equals 1. The authors impose constraints on the rise function ui, phi I, requiring it to be monotonically increasing and twice continuously differentiable, and that neuron potentials with ui, phi I, is greater than or equal to 0 are sensible to avoid physically implausible phase jumps. They illustrate the concept using the integrate and fire model, equation 21, and find a multiplicative coupling transfer function, equation 22. The authors also consider the Marollo-Strogatz neuron potential B, which does not lead to an affine transfer function with multiplicative coupling. Instead, they propose an alternative neuron potential, equation 24, which leads to an affine and even linear transfer function, equation 25, for multiplicative coupling. Notably, the authors demonstrate the equivalence of multiplicative and additive coupling, showing that both interaction mechanisms can be transferred into each other by simultaneously modifying the rise function accordingly, as described by equations 26 and 27. This highlights the flexibility of the coupling scheme and its potential applications in modeling complex oscillatory systems. A key concept in neuron modeling is the transformation between additive and multiplicative inhibitory pulse coupling. Recent research has demonstrated that, given a rise function u, phi, for additive coupling and a specific additive coupling strength epsilon, the coupling strength kappa of the transformed dynamics can be freely chosen, with the transformed rise function u determined accordingly. The mathematical foundation of this transformation is described by equations 30 and 33, which establish the equivalence of spiking dynamics under both types of couplings. The transformation from additive to multiplicative coupling is further illustrated through the analysis of two standard neuron models in Figure 3ac. A crucial aspect of this transformation is the relationship between the reset potential and the minimal allowed potential u, phi, equals 0, with being greater than 0. Consequently, the baseline potential equals 0 is always lower than the reset potential greater than 0. Equations 34 and 35 describe the actual neuron dynamics in terms of x, t, equals u, phi, t, and x, t, equals u, phi, t, respectively, under the assumption x, t, equals x, t, equals xthr equals 1. Furthermore, the authors demonstrate the applicability of this transformation to the standard leaky integrate and fire potential, equation 13, emphasizing that equivalent rise functions require the same period length t, which implies an equal phase velocity d phi, dt equals omega equals 1, t. By understanding this transformation, researchers can now easily translate dynamics from one coupling type to another, greatly facilitating the comparison of models with different types of coupling. This fundamental equivalence will help elucidate the neural code by making distinct modeling frameworks compatible, potentially paving the way for more unified and coherent interpretations of experimental results. In neural network models, transforming multiplicative coupling to additive coupling is made possible by the relationship between their rise functions, as expressed in equation 33. This equation enables the conversion of multiplicative coupling models into additive coupling models, provided the transformed rise function is strictly monotonous and continuous. To illustrate this transformation, two examples are presented. The first involves a standard leaky integrate and fire rise function for multiplicative coupling, with a corresponding transfer function. Applying the transformation yields an equivalent additive coupling rise function, shown in Figure 3gi. The second example considers a linear multiplicative coupling transfer function, resulting in an equivalent additive coupling rise function that is a shifted version of the Marollo-Strogatz neuron potential. Notably, the transformed rise functions can be approximated by rise functions that avoid divergent behavior as phi approaches 0, allowing for normalization to u, 0, equals 0. This method for transforming multiplicative coupling models into additive coupling models is crucial for understanding how different coupling mechanisms can be related and how their properties can be transferred between models. Figure 3 illustrates the transformation between additive and multiplicative pulse coupling, showcasing rise functions and transfer functions for various neuron models. The additive coupling rise function u, phi, and transfer function h, epsilon 1, phi, equals h kappa, phi, are depicted in subfigures a and b, respectively, while the multiplicative coupling rise function u, phi, is shown in subfigure c. This transformation is demonstrated for different neuron models, including the leaky integrate and fire neuron model with additive coupling, the Marollo-Strogatz neuron potential with additive coupling, the leaky integrate and fire neuron model with multiplicative coupling, and the neuron potential C with linear transfer function for multiplicative coupling. The discussion then shifts to inhomogeneous coupling strengths, where the equivalence between multiplicative and additive coupling is examined. By setting epsilon 1 ij is defined as epsilon 1 and kappa ij is defined as kappa, the previous sections assumed homogeneous coupling strengths, where the coupling strengths, epsilon 1 ij depend only on the receiving neuron I, not the sending neuron j. However, the equivalence holds for inhomogeneous coupling strengths and coupling topologies defined on networks. To achieve equivalent dynamics for variable original coupling strengths, the rise functions and coupling strengths are transformed via a mapping uniquely determined by defining two values of epsilon 1 and kappa as equivalent. This transformation is illustrated by equation 52, where u, phi, equals 1 kappa, 1 u, phi, epsilon 1. The corresponding transfer functions for additive and multiplicative coupling are equal not only for the specific choice of epsilon 1 and kappa used in the transformation but also for any combination of additive and multiplicative coupling strengths, epsilon 1 foot and kappa, that satisfy equation 53, kappa equals 1 kappa, epsilon 1 foot, epsilon 1. This result implies that for each neuron I, a single choice of two equivalent coupling strengths defines both the transformed rise function and the coupling strengths. Transforming standard additive coupling to multiplicative coupling is achieved through a mapping between equivalent coupling strengths, defined in terms of the reset voltage of the new rise function. This transformation is given by equations 54 and 55, where the new multiplicative coupling rise function is expressed as u, phi, equals u, 1 u, phi, and the mapping between equivalent coupling strengths is kappa ij equals 1 u, epsilon 1 ij. Conversely, transforming multiplicative coupling to additive coupling is achieved through equation 57, where epsilon 1 ij equals log 1 kappa ij, log u, phi 1. Interaction topologies defined on a directed graph can be implemented explicitly using an adjacency matrix or implicitly by setting epsilon 1 ij equals 0 or kappa ij equals 0 for unconnected neurons. An example of delayed heterogeneous coupling on a directed network is presented, demonstrating the transformation of multiplicative to additive pulse coupling in a winners-take-all (KWTA) computation based on a network of inhibitory coupled oscillatory neurons. The free dynamics of each neuron are defined by differential equation 58, with a reset rule that sets the neuron state variable to 0 when it reaches a threshold. The interaction between neurons is given by all-to-all inhibitory multiplicative pulse coupling, as expressed in equation 60. To perform KWTA computations, the functions xi, t, that set the intrinsic frequencies of the individual neurons are interpreted as the time-dependent input of the network, while the stream of reset events defines the output space. The system converges to a periodic orbit, where only the K neurons with the largest intrinsic frequencies spike, revealing the subset of the K largest input signals Xi. The equivalent dynamics for additive coupling are implemented through a free neuron dynamic given by equation 63, which corresponds to an additive coupling rise function expressed in equation 64. The shape of the rise function does not change with Xi, t, but the intrinsic neuron frequency does. The original multiplicative coupling formulation is illustrated in Figure 4, with typical dynamics shown in Figures 4D and 4E. The equivalent additive coupling dynamics are shown in Figures 4G and 4H. This transformation between equivalent coupling strengths is crucial, as it allows for the conversion between multiplicative and additive coupling, enabling the implementation of complex neural networks with varying coupling strengths. In Figure 4, we illustrate the reconfigurable winner-takes-all (KWTA) computation via symmetrical inhibitory coupling for multiplicative and additive coupling. This network consists of n equals 5 oscillatory neurons with time-dependent external inputs Xi, t, setting the intrinsic frequencies of the individual neurons. The choice of Xi for the illustrated dynamics is shown in Figure 4b. The rise functions for multiplicative, additive, and approximated additive coupling with UAPP 0 equals 0 are depicted in Figure 4c, f, and I, respectively. For multiplicative coupling, the equivalent dynamics with K equals 2 and K equals 3 spiking neurons are shown in Figure 4D and E, respectively. The coupling strength kappa is set to 0.21 for the first orbit, K equals 2, and 0.19 for the second orbit, K equals 3. For additive coupling, the equivalent dynamics with K equals 2 and K equals 3 spiking neurons are shown in Figure 4G and H, respectively. The coupling strength epsilon 1 is set to 0.1 for the first orbit, K equals 2, and approximately 0.089 for the second orbit, K equals 3. The relationship between multiplicative and additive coupling strengths is given by kappa equals 0.19 for the second orbit, with K equals 3 is equivalent to epsilon 1 foot approximately equals 0.089, as shown in equation 53. Figure 4ik illustrates how additive coupling with U, 0, equals equals infinity can be effectively approximated by a modified additive coupling rise function UAPP, phi, that satisfies UAPP, 0, equals 0 for a more practical implementation. The minimal phase reached upon inhibition is larger than delta equals 0.2. Making the illustrated spiking dynamics fully equivalent to both the original multiplicative and exact additive transformation. This is achieved by defining UAPP, phi, for phi less than delta in terms of cubic extrapolation, which satisfies UAPP, 0, equals 0. The second example considers a network with delayed, heterogeneous coupling, implementing a phenomenon initially addressed in 31. The network consists of n identical oscillatory neurons with a leaky integrate and fire dynamic, given by equation 65. The interaction between different units is given in terms of delayed inhibitory additive pulse coupling, as shown in equation 67. The coupling strengths epsilon 1ij are given in terms of the adjacency matrix A of a directed graph with matrix elements I element of 0, 1, as epsilon 1ij equals epsilon 1i, Gi, where Gi is the integree of node I and epsilon 1 greater than 0 is a global constant. Figure 5a and b depict two interaction graphs, G and G, which are identical except for an additional directed link between neurons 1 and 5 in the second graph. The network dynamics are described by equations 65 and 67, which govern the time evolution of the neurons and the interaction between them, respectively. The relationship between the coupling strengths and the network topology is given by equation 68, which shows that the coupling strengths are proportional to the integree of each node. The dynamics of the network are influenced by the topology of the interaction graph, as shown in Figure 5. The addition of a directed link between neurons 1 and 5 in graph G changes the synchronization properties of the network. This demonstrates the phenomenon of topology-induced synchronization, where the network topology affects the collective dynamics of the neurons. Figure 5 illustrates the phenomenon of topology-induced phase synchronization via inhibitory coupling with delay. The network initially consists of n equals 10 identical integrate and fire neurons with an interaction topology defined by graph G. The strongly connected components A and B influence component C independently, resulting in partial phase synchronization. The introduction of a directed link from node 1 to 5 transforms the interaction graph to G, where A becomes the autonomous source of the system, synchronizing and imposing its phase on the rest of the network through directed connections. This effect is evident from the phase lag of individual units relative to the collective dynamics period length t, as shown in figures 5e and 5f. The equivalent rise functions u, phi, and u, phi, for additive and multiplicative pulse coupling are presented in figures 5c and 5 grams, respectively. The equivalent coupling strengths, epsilon 1ij and kappa ij for additive and multiplicative coupling are depicted in figures 5d and 5h, with the added links matrix element marked by a blue square. The phase formalism for the original additive coupling is derived, yielding rise functions ui, phi, and transfer functions hifi, epsilon 1ij, phi I, as given by equations 69 and 70. Since the neurons are identical in their free dynamics, differing only in coupling strengths and transfer functions, using multiplicative coupling requires identical free dynamics but different coupling strengths kappa ij for each pulse-receiving neuron I. A constant reset voltage equals U, 0, greater than 0 is set to is defined as 0.1 for all neurons, used to define the transformation to multiplicative coupling, as seen in equation 37. In the realm of spiking neural networks, interactions are typically modeled as either additive or multiplicative. Additive models describe postsynaptic responses in terms of coupling strength, while more advanced models employ state-dependent changes in response to incoming pulses. This difference can be examined mathematically using a framework involving equivalent rise functions. The rise dynamics, xi, t, and associated multiplicative coupling can be equivalently formulated using u, 1i, gamma, 1e caret, gamma t, in equation 71, where gamma characterizes the instantaneous, or delta-coupled postsynaptic responses with homogeneous inhibitory coupling. An alternative framework, expressed in equation 72, for ui, phi I, utilizes u, 1, I, gamma, 1 gamma, 1, I phi I. Comparisons are shown in figure 5, G, further highlighted with respect to figure 5, D, H. Degree of phase locking assessments will necessarily then utilize spike and rising phase interaction equivalents due to adjusted effective single coupling equations, or variants formulated such that respective neuronal voltages shift. Resultant oscillation modeling performance similarity corresponds despite formal seeming disconnectivity underlying forms investigated between current more reduced complex potential simulations relative advanced analyses. The correspondence relationships among formally opposing varieties of additive and multiplicative interactions were detailed fully initially and seen effectively relative to those via not originally one presented simply resultant varying general common general result varying investigated theory relationships. Additive, multiplicative correspondence transformations remain advanced topics originally appearing in dynamic connection change class differences relationship across different standard applications, especially compared to the formulation that can characterize transfer that interaction dynamical, like such previously researched comparisons result discussion type established interactions. Synchronization in networks of pulse-coupled oscillators with delayed pulse coupling is a complex phenomenon that has been extensively studied. Building upon previous research, which demonstrated the existence and robustness of unstable attractors in such networks, this study delves into the concept of topological speed limits to network synchronization. This concept, explored in earlier works, reveals the intricate relationship between network topology and synchronization dynamics. The breakdown of order preservation in symmetric oscillator networks with pulse coupling is also examined, highlighting the importance of understanding the interplay between network symmetry and synchronization. Furthermore, the study touches upon isochronous dynamics in pulse-coupled oscillator networks with delay, which has significant implications for our comprehension of rhythm generation in biological systems. The Hodgkin-Huxley model, a quantitative description of membrane current and its application to conduction and excitation in nerve, serves as a foundation for understanding the behavior of biological oscillators. The work of Winfrey on biological rhythms and the behavior of populations of coupled oscillators provides valuable insights into the synchronization of oscillatory systems. Additionally, Erman-Trout's study on type 1 membranes, phase resetting curves, and synchrony offers a deeper understanding of the mechanisms underlying synchronization. The importance of simulation tools for spiking neurons is also emphasized, as highlighted in a review by Brett et al. These tools enable researchers to model and analyze complex neural networks, facilitating the discovery of novel synchronization mechanisms. By synthesizing these concepts and findings, this study provides a comprehensive framework for understanding synchronization in networks of pulse-coupled oscillators with delayed pulse coupling.